Okay, so we're going to be looking at section 1.4, which is about the matrix equation, or AX equals B. Okay, so in my AX equals B equation here, X is a vector and B is a vector. Well, A is a matrix. Okay, we talked about how last time we only add and subtract vectors, we didn't multiply them. Okay, we're going to look at matrix multiplication in this section and see how it applies to linear systems. Okay, so if a matrix A, if A is an m by n matrix, okay, so m by n rows by columns, okay, m by n matrix with columns a1 through an, because remember there are n rows, so we should have n such columns, okay, and knowing what we know about columns, right, a matrix with one column is a column vector, okay, so we can consider that a vector as well as a column of our matrix. Okay. And then X is a vector in Rn. So remember, however many coordinates your vector has corresponds to which space that vector is in. So Rn in this case. Then Ax, and again, X is a vector, A is a matrix, is the linear combination of the columns of A with the weights or linear weights corresponding to the values in the vector X. Okay, so let's look at what that means, right? So I'm going to have a matrix here, 1, 2, 3, negative 1, 0, 1, and 2, 3, negative 1. Okay, so I have my 3 by 3 matrix there. Okay, so that's my matrix A. My vector X, I'm going to just do x1, x2, x3. So they're going to be unknown variables. Okay, so if I multiply these two, okay, and so you're asking, well, we don't have a direction for how to multiply matrices yet. Okay, and that's a true statement. So that's what we're going to look at next. So when I multiply a matrix, I go across the first row and down the column. Okay, so that same movement there, across the first input, down the second. Okay, so when I'm multiplying here, I would have 1 times x1, so I get x1. 2 times x2 is my next one, so plus 2x2. And then 3 times x3, so plus 3x3. Okay, then I go to the second row. So I go to the second row of my output here in my equation. So negative x1, so I'm going to have negative 1 times x1. 0x2, so I'll leave it off. And then 1x3, so plus x3. Then third, I've got 2x1, 3x2, and negative x3. And that itself is a vector. It's a column vector. Okay, so we will call it B in my equation here, AX equals B. Okay, so when you're multiplying matrices, you go across and down. Okay, across and down. So this matrix B is a linear combination of these columns of A. Okay. So pick your favorite vector over here to be B. Let's say 1, 1, 1. Okay. Now, if you look at this right-hand part here, and so this 1, 1, 1 vector is just an arbitrary vector that I chose to be equal. If you look at this right-hand part, this is a system of equations, right? It's 2 column vectors. They're only equal if the components are equal. So I could actually set up a system of equations that looks exactly the same, right? This would be x1 plus 2x2 plus 3x3 equal to 1. Negative x1 plus x3 also equal to 1. And then 2x1 plus 3x2 minus x3 equal to 1. And that would be a system of equations. So there would also be a corresponding augmented matrix, right? This would be 1, 2, 3, 1. 1, 0, 1, 1, 2, 3, negative 1, 1. And so that's going to be an augmented matrix. Right? So the augmented matrix here corresponds to the matrix equation, and you could even make a vector equation that would correspond to this as well, right? Because ultimately what we did here is I took x1 and multiplied it by this first vector, and x2 and multiplied it by this second vector, and x3 and multiplied it by this third vector. So this would be the same thing as the vector equation x1, 1, negative 1, 2, x2, 2, 0, 3, x3 with 3, 1, negative 1, and setting that equal to 1, 1, 1. Okay, so all of these representations correspond to the same system and a lot of the same information. Okay, we just talk about it in a slightly different way. So this again would mean that this 1, 1, 1, based on the last section, is a linear combination of these three vectors, assuming we can find values for x1, x2, and x3. Okay, and again, I promise I'll do some calculator examples with you. So if you go to your calculator here, standard TI-83, again, go over to edit. So we're going to have a 3 by 4 matrix, right? Looking at my augmented matrix here. I'm going to have 1, 2, 3, and then 1 in the fourth column. Negative 1, 0, 1, 1 again in the fourth column. 2, 3, negative 1, 1 in the fourth column. Okay, go back to your main screen. And again, I'm going to go up to matrix, go to math, go down to B for RREF, or reduced row echelon form, and take the reduced row echelon form of the matrix A, and there's our reduced matrix. So we see here that x1 should be equal to negative 1, x2 should be equal to 1, and x3 should be equal to 0. Okay, there are no free variables, so we don't have any issues. We have a unique solution, and a solution exists. Okay, so we could solve this solution for this system, I should say, with x1 equal negative 1, x2 equal 1, and x3 equals 0 would be the unique solution for that system. Whether or not you think of that system as a matrix equation, a vector equation, or an augmented matrix, okay? Each one gets us to the same spot, okay? Now, notice what I said where I said when we're multiplying matrices, we go across the first rows and down the column in the second entry, okay? So if I'm multiplying a matrix or a column vector, which ultimately is just a one column matrix, and I have something that looks like this: 2, 4, negative 1, 0, negative 10, 6, and I try to multiply that by just x1, x2. Okay, so as I'm going across here, 2 times x1, okay, 4 times x2, but then I would get to this third spot, and I don't have anything to multiply it by. So when you're multiplying matrices, you have to have the same number of columns in the first one as you do rows in the second one. Okay, so your number of columns here has to match up to the number of entries in that multiplication vector. So we can't do this. What we could do is multiply it by a column vector in R3. So x1, x2, x3 now. Okay, so now I've got 3 columns here, and I've got 3 entries in my vector, or 3 rows in my 1 column vector. So if I multiply here, I would get 2x1 plus 4x2 minus x3. And then I would have negative 10x2 because I had 0x1 plus 6x3. And that would be my column vector. Okay. And I could actually set that equal to something again and solve the system, right? So set this equal to your favorite vector, 2, 3, 4, 5, whatever it might be. Right? And then you could set up an augmented matrix, right? Our augmented matrix, right, would have whatever my favorite vector that I put there. I gave it B1, B2, since in the matrix equation, a lot of times we call it vector B. Okay, and so this vector B is a linear combination of the vectors here. Okay, So matrix equations go with vector equations. Okay, so let's look at one here. 2, 0, 4, negative 10, 1, 6, negative 1, 6. Use that same matrix I was just using there. And let's multiply that by 4, 3, 7. Okay, so I can go through and do this multiplication. 2 times 4 is 8. 3 times 4 is 12, so that's 20. And then 1 times negative 1 times 7 is a negative 7, so I get 20 minus 7, I get 13. Second row here, I get 0 times 4 is 0. Negative 10 times 3 is a negative 30. 7 times 6 is 42, so I have negative 30 and a positive 42. That's going to make 12. Okay, so my vector 13, 12 is a linear combination of these columns. So let's label these columns A1, A2, and A3. We'll call this one B. So this is my vector X, right, in my matrix equation AX equals B. So B is a linear combination of A1, A2, and A3. Okay, which also means that B is in the span of those vectors. Okay, I know there's a lot of similar terminology that tends to refer to a lot of the same things, okay, but we just have to keep it straight in our mind. And yes, many times it does refer to the same thing. There's a lot of overlap in the definitions and terminology in linear algebra, okay, because we use all these things in concert. Matrix equations, vector equations, augmented matrix, they all work together to get us the results that we are interested in or that we're looking for, okay? So matrices and matrix equations and vector equations tie directly together, okay? So you're looking at linear combinations, okay? That's what we will deal with. Okay, and so the book talks about a row vector rule for computing AX, okay, a row vector rule. Okay, so a row vector rule. So the row vector rule says that if product AX, and again, X is a vector, A is a matrix, is defined, then the ith entry in AX, the ith entry in AX is the sum of the products of corresponding entries from row I of matrix A and the vector X. So this is just a rule that explains what we've been talking about, how you go across the row of the first entry and down the column of the column vector. Okay, so if you have a simple 2 by 2 matrix, which I'll just label with A, B, C, D, and X1, X2, the row vector rule just says that I multiply the products in the corresponding positions, and I get the corresponding result. So I would get A X1 plus B X2. In the second, I would get C X1 plus D X2, which I could also write as a vector equation, which would have X1 with AC, not 9, that's an A, and it would have X2 with the vector BD. Okay, so we can use those rows and vectors interchangeably, okay, all the way through. Okay, again, there's several other examples in the book that you can look at, see how those work out. Use the homework to your advantage to work through the pieces there, okay? Now we do have a couple of properties for matrix multiplication, matrix vector multiplication. So properties. Okay, the first one is that we have distributivity. So if I have A times U plus V, I can do AU and AV. So my U and V here in this property are vectors. My A again is a matrix. And I also have scalar associativity. So if I have A times CU, I can write that as C times AU. Okay, so we have distributivity and associativity as it pertains to these vector multiplications. Okay. Now, when you're thinking about these linear combinations and these spans, okay, if I have two vectors in R2, so pick your favorite two vectors in R2, let's say 2, 1, and 4, 5. Okay. If I set up a system here, 2, 1, right, and I augment that with some unknown vector B, okay, and I start row reducing that, right? So I divide that first row by 2, 1, 2, B1 divided by 2. This would be 1, 5, B2, right? I scaled that column. Then maybe I go subtract. So I took row 1 and divided it by 2 and replace row 1. Now I'm going to take row 1, negative row 1, add it to row 2 and replace row 2 because I got my 1 in the upper left. I want to get a 0 below it. Okay, so I take 1, 2, and B1 divided by 2 is taken care of. 1 and negative 1 makes 0. Negative 2 and 5 is going to be 3. Then I'm going to have B2 not divided by anything just yet. So just B2. Got ahead of myself. Let me try that again. So negative B1 over 2 plus B2. Okay, and I could divide this by 3 and scale that. And so I see I'd have a triangular matrix. So I have a solution of any kind. Now the B1s and B2s would change. Okay. But if I'm able to reduce this to where I have no free variables, then that means I cover the entire space. Okay. So since I have no free variables, that means the span of U and V is equal to all of R2. Okay. Now, if you have a free variable, then you have less than that. You also have to be careful of not having enough vectors. So let's say I go to 4 dimensions, 1, 2, 3, 4. So I make my vectors U and V in R4 now. Okay, well, if you set up a system with this, you will find that there are no free variables. Okay, those two vectors don't go in the same direction, right? Think geometrically, when they went in the same direction, they made just a line. Okay, so those vectors don't go in the same direction, but there's not enough of them to be R4. Right, so the span of U and V can't be all of R4 because I would need 4 vectors to do that. Okay, so you have to have enough vectors. If you're in R2, you need at least 2 vectors. If you're in R4, you need at least 4 vectors. If you're in R5, you need at least 5 vectors. Okay, but just because you have that many vectors doesn't guarantee anything, right? So if I take another set of U and V, similar to like I did in the last section, so if I have U and V, which is 1, 2 for U, and then V, I make negative 1, negative 2. Okay, well now V is actually a multiple of U. It's just negative U. So what that means is the span of U and V is actually the same as the span of just the vector U. Okay, because it doesn't cover anything additional, right? The vector U gives you a line through the origin. The vector V is still on that line, so you don't get any new space. So the span of U and V is not all of R2, okay, because it doesn't give you that additional dimension. So you need at least that many vectors, but you also need there to be no free variables, okay? Because if you set up a matrix here with those two vectors U and V, okay, if you row reduce that, you will find that you do not get that you get a free variable is what I want to say, right? So you can actually do that in your calculator again, trying to show you those examples as I get to them. So here I'm just going to take a 2 by 2 matrix, 1, -1, 2, and -2. And again, I'm going to reduce row echelon form that. You see I get 1, -1, 0, 0. So again, I don't have that triangular form here. I don't have that 1. This actually is triangular. But I don't have that pretty ones along the diagonal that I can easily read off the variables. I have a free variable because there is no pivot in the second column. Okay, so if you have a free variable, you can't cover all of the space that way either. Okay, so a few different things there. But again, they all relate together. They all tie together. Okay. Okay, and so that's going to finish up what I want to talk about in this section here. I am going to switch over a little bit to the textbook just to point some things out to you to hopefully help you in your preparation, looking at homework and getting you ready for the quizzes and tests and those checks for understanding as well. Those true-false questions that you do in D2L. So I'm going to just bounce over to that screen share with the textbook. Okay, so we take a look at our text here. There's these 3 practice problems at the end of this section. There's practice problems at the end of every section. Sometimes there's 2, 4 different numbers, but there's 3 at the end of this section that I think are very beneficial. If you will look at those, work through those in the way you do. So you see that we have a matrix A, and a vector P here, and then a vector B that it sticks out. So it says, it can be shown that P is a solution of AX equals B. Use this fact to exhibit B as a specific linear combination of the columns of A. So I have columns here of A, 4 columns, and I have 4 entries in P. So it means I can do A times P because I have 4 entries and 4 columns, so that works out. And if I do A times P, then I can find B. Okay, which means that using our row vector property, these are the linear weights accordingly. Okay, so you can set up this system, right? If you use a x vector, x1, x2, x3, x4 with A, and you multiply, you could set up an augmented matrix and then find values for x1, x2, x3, and x4. Okay, and that will hopefully help you see kind of the way those matrix multiplications work. Okay. 2 then talks about verifying that when you add, so that gives you a couple of computations you can do. And then 3 sort of flips the problem around, asking you to construct a matrix that works. The other thing that's nice about these practice problems that are at the end of every section, not just this 1.4, but they're at the end of every section, so you can use those, is that if you scroll to the end of the exercises, it takes me a couple pages to get there, you'll see that the solutions to the practice problems are actually here at the end of the section, okay? So you can work those and then use those solutions, figure out kind of where you might go right or wrong, things like that, okay? And again, take a look at the homework. You know, you're always welcome to contact me, see what you need help with, and I am happy to help facilitate that, okay? So thank you for joining us. I'll be over on 1.5 next, which will talk about solution sets.